on fluids. And this will be dealing with liquids and gases, right, and properties of them, as we'll see. So we'll be dealing with pressure, get into that, density, buoyancy, Bernoulli's principle, and so on. So that's going to be the chapter here. As far as that's concerned, we're skipping chapter 9, so our next exam 4 will be on chapters 10 and 11. So with no further ado, move into here. We'll talk about liquids and gases. We talk about density. All right, this is the Greek letter rho, and it's mass over volume. And this will either be in kilograms per cubic meter or grams per cubic centimeter. All right. So the table 10.1 has some characteristics of different densities of liquids and gases. Solids, we have that too, but for this lab, we're pretty much going to be dealing with densities of liquids and gases primarily, but solids are generally the densest, followed by liquids, followed by gases. All right, so as we're going to be using more commonly water, H2O, and the density of water in units of SI units is 1,000 kilograms per cubic meter. In units of CGS units, gram centimeter seconds, it's 1 gram per cubic centimeter. So these are interchangeable, just the units are different as far as that's concerned. While we're on this, so that's water. As we're on here, let's see, what do I have? All right, ice. So this is as a liquid. So this is water. As we'll see, ice has a density of 917 kilograms per cubic centimeter, or 0.917. And we could also refer to this relative to the density of water as the specific gravity. So we don't have a unit with this when we talk about specific gravity, because we're comparing the density of the object to the density of water. While we're on this, density of air is approximately 1.29 kilograms per cubic meter. So the density of air in this room, if you have 1 cubic meter, a meter by meter by meter, weighs about 1.29 kilograms. So it's about 1,000th the density of water. And this is at sea level. Now, while we're comparing liquids and gases, one important point here will be that a liquid is basically incompressible. unlike a gas, which can be compressed. And what does this mean? All right, so we take water. All right, density of water is approximately 1,000 kilograms per cubic centimeter, 1 gram per cubic. At sea level, you go down to the bottom of the Mariana Trench, which is about 36,000 feet, 6 miles, 7 miles. The density of the water is basically the same as it's here. Basically, liquids and solid are incompressible. The pressure, as we'll see, goes up because the pressure is based on the weight, but the volume itself, the density, is not changing. Air, on the other hand, gases are compressible. And that's what we'll see when we talk about pressure. Pressure is based on the weight of everything above it. So the density of air and the pressure, when we get into that, is based on all the weight of the air above it. So as we go higher and higher and higher in altitude, air becomes less dense. It actually turns out to be cooler, and the pressure becomes less. And so the pressure increases in depth, but liquids are incompressible. So we'll keep that in mind there. Okay? So that's the first part of chapter 10. This is actually be section 10.2 as far as that's concerned. Okay. So I'm going to move on to fluids pressure now and define that. So I'll leave this up here for a minute before I go on. If you get it. All right. So, pressure. Pressure is defined as P, and this is given as force over area. So this is, we have an object, all right? Let's say 1 meter on each side. So it has a cross-sectional area, and this is a meter squared. And say this object weighs 10 kilograms. This will have a weight force of mg, or approximately 100 newtons. So if we have a 10 kilogram weight spread over 1 meter, it will exert a pressure of 100 newtons over 1 meter squared, which is 100 newtons per meter squared, which is also given the unit Pascal. All right, so that's the unit of Pascal, named after Blaise Pascal, famous 17th century scientist who realized that the air pressure as we went up in altitude became less and less and less, which is an important concept to understand the atmosphere and weather. All right, so that's what we define pressure as. If we have a smaller thing, say we have a 10 kilogram object, but instead of spread out over certain distance, it weighs 10 kilograms, but instead of that 1 meter, it's spread out exerted over 10 kilograms, 1 centimeter on each side. Well, that area is going to be, the area is length times width, 0.01 times 0.01, which would be 10 to the minus 4th meters squared. Therefore, the pressure in that case will be still 100 newtons times 10 to the minus 4th, which would then be 10 to the 6th pascals, which is that's a very high pressure. So if we have the same weight over a much smaller area, we have a much greater pressure. So that's the concept there as far as that's concerned. Okay. All right. Now, as you can see, this only depends on depth. So we're going to be now moving into liquids. So we have a solid, that exerts pressure on something. All right. Now let's move on to liquids, because we're going to be dealing with primarily water. All right. So we're going to be using water, H2O, which has a density, again, the Greek letter, of 1,000 kilograms per cubic meter. Now, the density of water does vary slightly if you go in temperature, as we'll see later on a little bit when we get into temperature laws, gas laws. It gets interesting what the density of water is near the freezing point. So for now, we're just going to deal with that. All right, so what do we have? If we have a container, all right, let me actually fill this up over here. Okay. This water has a density of 1,000 kilograms per cubic meter, and if we have water, all right, then what we have is at say the bottom of this, and this thing is approximately, the depth of this is approximately 10 centimeters, which is 0.1 meters. All right. If we have something on the surface, all right, the only thing we're going to neglect air pressure for the moment, because air exerts pressure because of the weight above it. But on the bottom, if this thing is on the bottom, there's an air pressure being exerted on it. There's water pressure, I'd say, based on the mass of water above that. And how do we calculate that pressure? Pressure is defined as, in a liquid, is the density times G, which in this case is 9.8 meters per second squared, but we're going to use roughly 10 meters per second squared, times the depth. So the depth that we are below the water in meters. So this will be in meters. So this will be 1,000 times 10 times H, which is roughly 10,000 times H in units of meters, and this will be in units of pascals. So for water, within a reasonable range of temperature, again, liquid, the pressure goes as 10,000 times the depth in meters. All right. Now, how can we calculate? So to calculate this, the pressure for 0.1 meters down would be 10,000 times 0.1 would be 1,000 pascals, PA. So that would be the pressure on this little piece of metal at that point. Okay. So that'd be it there. Besides that, though, there is also the pressure of the air above that. So what really would be the pressure on this object? And part of what we'll get into this is I have a scuba diving license. So part of it, understanding to get the license to be able to go scuba diving safely, is to understand pressure of air and water as you go down in depth. Unless you understand that, you can have significant problems. If you stay near the surface, it's not a big deal. You go farther down, you got to deal with pressure. And how does it actually matter? So we're going to go into that next. So again, this is part of section 10.3 in the text, and also 10.4. All right, so this is what we have. This is our expressions. So before I get to that, here's what we have. Now, if we have atmosphere, right? The atmosphere. And you take, and I know from my old measurement, you take 1 square inch on surface, all the weight of all the air above that has a weight of 1 square inch, has a weight of about 14.7 pounds. This is how I learned it. All the weight about 14.7 pounds. You go higher, higher. This is the pressure. This is what we call 1 atmosphere, ATM. So that's in English units. However, for most of the problems, and it's much easier, we will do it in units of SI units. And it turns out that 1 atmosphere, ATM, is equal to 101,001 times 10 to the 5th pascals. That is 1 atmosphere. So 101,000 pascals. So roughly 100,000 pascals are 1 atmosphere pressure. That's what it weighs there. All right, so back to the original problem here. Then the actual pressure on this thing is this 1,000 pascals being down 0.1 meters plus the weight of the atmosphere above it. So the actual pressure is going to be P P of H2O plus P of atmosphere. All right? So the actual pressure will be 101,000 plus 1,000, or roughly 102,000 pascals. All right. So that would be there. So the actual pressure is the pressure of the atmosphere plus that. So if we're at near sea level, you're always getting to that plus the depth of water. So part of the question comes into is, how do we use water depth and pressure compared to atmospheric pressure? How far down do we have to go so that the pressure of the water is equal to the pressure of the atmosphere? All right. So I'll use this here, use my expression here. And again, for purposes of simplicity, the P atmosphere is roughly 100,000 pascals. So this is P of H2O. I'll just put that in there. All right, how far do we have to go down for the water pressure to equal the atmospheric pressure? Well, we'd have to go is we'd have P H2O equals P atmosphere equals 10 to the 5th. Again, we're just being approximate. We don't need to be exact. Is about 10,000 times H. Now, if we solve for H, that would mean H is about 10 meters. So what this means is if we have a column of water 10 meters deep, the pressure, so the pressure of the water itself is going to be 1 atmosphere. So then the total pressure will be 2 atmospheres. So for 10 meters, so for H is 10 meters, then total P will be P of atmosphere plus P of H2O will be 10 to the 5th plus 10 to the 5th is 2 atmospheres. Be careful, don't add that into 10 to the 10. So it'll be 10. So every 10 meters you go down, you add 1 atmosphere pressure. So starting from the surface, we have 1 atmosphere pressure. We go down 10 meters, we go down far enough, it'd be 10 plus 10. You go down another 10 meters, it'd be 10 plus 20, 10 plus 30, and so on. So that's how pressure works. Now realize here, this only depends on the depth. It has absolutely nothing to do with how wide the container is. So if I have this as a tube and go down 10 meters, the pressure at 10 meters, if I have this long enough, would be the same as if I went 10 meters down on Lake Bemidji. So it has nothing to do with the size of that. And this is important for a lot of characteristics. All right, so that it only has to do with the depth, not the size of it. And this reminds me of when I would be doing some construction work a little bit on my own. As far as, I remember had to make a slab for a garage I was making. And, you know, it's going to be about 10 feet by 20 feet, so it's rather sizable, but it was only going to be about 6 inches deep for the slab. Well, I mean, it's big, and concrete is thick and dense, and it was still liquid. I thought, well, how big do I have to make the posts? How thick do I have to do that to make it work? Well, I realized it's only going to be this deep, so the amount of pressure here at the bottom is going to be relatively small. So all I just used was straight 2x4s, just one all laid out, and that worked just fine. On the other hand, I've seen examples where somebody they're going to pour a concrete wall, and it's relatively thin. It's only maybe a foot thick, but it's going to be like 10 feet high, and they brace it all the way equally from top to bottom, but not doing the bottom strong enough. Well, what happens is the pressure only depends on that. 10 feet is a lot, especially with concrete. You'll start getting a huge pressure at the bottom, and it'll start squeezing the stuff out. So the pressure, so you can be confused by having an example. Well, it's not very much material, but the depth is what makes a difference. So that's where this comes into play, rho g times h, right? So every 10 meters, and this is what we'll be using for that case. Exactly, all right. Now, we also get into pressure, and we'll leave it at that. But a couple other things as far as units, to be exact. So 1 atmosphere is 101,000 pascals Or in weather, which we're not going to get into, it's also equal to 1,013 millibars. All right. Weather maps use bars and millibars for markers. It's nice and convenient. So 1 atmosphere pressure at sea level is about 1,013 millibars. This is not a meteorology class, but that's what we use there. All right, so that's section 10.4. One more thing here, I'll do Pascal's principle and move on to the last section of Archimedes Principle. And so Pascal's principle is if we have say we're trying to lift a car, like a big jack. So you got a car, all right? And you have a hydraulic system where they try to jack it up like an auto body shop. You have liquid here. So we put a force here, A, and we have a force B here. And a car, which weighs 1,000 kilograms, which is approximately 10,000 newtons, right? And then if you have a size here of, say, 2 meters on each side, so we have a big liquid, so the area of this is, say, 2 by 2, so 4 meters squared. And then the other hand, we have this only being 10 centimeters on each side. So 10 by 10, or 0.1 times 0.1, which is 0.01 meters squared. What we're going to see is, given the relationship of, this is area A, this is area B, FA over area A equals FB times area B. And what we're going to see is you can have a relatively small force, because the pressure is the same on that, lift a much higher thing. Now this is going to have to move much more to raise that. What we can see is how much force can actually be. Then FA will be FB times FA, area A over area B, which would be 10 to the 4th times 0.01 times 4. That would be, let's see, 10 to the 2nd, or 20 over 4. That would be 25 newtons. So about 2.5 kilograms. So a force of 25 newtons can lift a 1,000 kilogram or 10,000 Newton car by this hydraulic means. So this is hydraulics. Now to make this actually work, for this to raise a amount, this will have to go much, much farther, because there's much more volume here is there. So that's Pascal's principle. We'll just, so this is the relationship of that. So we have F of A, area of A equals F of B times area of B. So this will be in newtons. This is in meters squared. All right, so that's Pascal's principle. Last part, that's section 10.5, right? All right, so last thing we do here, and this is also the basis of lab 9, and then I'll go into Bernoulli's principle on next lecture. All right. Okay, so what we have here. So we're skipping section 10.6 on gauges. This is section 10.7 on buoyancy and Archimedes Principle. And this is also the basis of lab 9, which you'll see a lot of it. So, what have we got here? All right, Archimedes Principle is, all right, so for Archimedes Principle, again, the basis of lab is that what Archimedes realized back in the 2nd century BC was that if we have an object, we weigh an object in air, such as this brass cylinder. It weighs approximately 100, and we're just going to deal with mass. So this has a mass approximately 140 grams in air. 140 grams in air. If we put this in water, it's going to displace. Notice the water level will go up slightly, and the amount of force it takes to raise that water is dependent directly on the volume of water displaced. And then based on that, we're going to see is we can find density from this. So this was discovered a long time ago. Archimedes was asked by a king in Greece to verify that the crown that was made for him was made out of pure gold and not mixed with lead to devalue it. And Archimedes was thinking and thinking, well, the easiest thing would be to melt it down and into a cube, weigh it, and get the density that way. But he couldn't destroy it. So he was thinking and thinking, and he could weigh it easy enough, because again, density is mass over volume. He could weigh it easy, trouble was to figure out the volume. What he realized is when he went into a bathtub one time, he sank in the water level was up, and all of a sudden it occurred to him, he discovered how to figure out the volume, and from there the density. And he apparently got out, ran through the streets of Athens naked, shouting, "Eureka, Eureka, I've discovered it." So this is what he did. So we have the mass, so we have downwards is we have the weight on it. Pushing upwards is the buoyant force. And the difference of the two, so we call this the apparent weight, will be the force of the weight minus the buoyant force. And this is Archimedes' principle. Now the lab 9 gets into more details of this. I'm going to go into a little bit shorter explanation as far as what we have here. So when we sink this, the amount of water displaced is equal to the volume of the cylinder. So we're going to do an example here then. If the object sinks, then on section 10.7, what we're going to have is we can calculate the density, right? density of the object compared to the density of H2O, which again, density of H2O is 1 gram per cubic centimeter, is given by the weight in air minus, divided by the weight in air minus the apparent weight. All right, so let's do an example here. Okay, this brass in air weighs approximately 132 grams, roughly. That's about right. Yep. I put it in the water, and it weighs less. How much does it weigh now? It weighs approximately, looks like 120 grams. Right? The apparent weight in the water is 120 grams. So what is the density going to be? Because this is 1, so the density will be 132 over 132 minus 120, which would be 132 over 12, which is roughly 11 grams per cubic centimeter. That would be the density. That's fairly close. Density of brass is approximately 9 or so. So it's pretty close to that. So that's how we do it. We weigh it. Here's our expression here. Weigh it in air, weigh it in the water. The difference is going to, the weight divided by the difference will give us our density. Let's try one more example. I have an aluminum block, and aluminum is less dense than water for the most part, less dense than most liquids. So what we have here is this thing weighs, looks like 125 grams, right? Roughly. All right, now we're going to weigh it in the air, water. Now, looks like it's 75 grams. In the water, it's 75 grams. So, what will be the density of this thing? So it's aluminum. It'll be 125 over 125 minus 75 is 125 over 50, or roughly 2.5 grams per cubic centimeter, which is very close to the actual value for aluminum. So that's the dense. That's how we can find the density of an object less than that weighs. I say density greater than water. All right, how do we do something that's weighs less than water? Okay. Okay. All right. In that case, let's do this block, right? This wood block floats. Right? Not quite stable, but it floats. So how do we can't, the apparent weight in water would be 0, but it doesn't mean there's no density. In that case, we have to do is look at something different. And in that case, we have the height of the block. And it turns out that the density is going to be related to the proportion of the block that's submerged relative to its height. So here's our thing for an object that weighs more than has density greater than water. All we're going to do is if it floats. Okay. So in that case, the height of this block, measured before, the height is 8.7 centimeters. Again, we use this in the lab, all right? And what it'll turn out to be is the volume of the object, or, right, the density. So what we're going to have is the depth divided by the height will be the density of the object divided by the density of H2O. And since this is 1, this will be the density of the object. So it'll be the density or depth of how much is submerged. So if it was equal to it, if this had the density of water, it would float right at the surface. But in this case, only this much survived, so we're going to measure how much is down below the surface. And that is hopefully, let's do it this way. This is 4.5. So this would be 4.5 over 8.7, or roughly, let's get exact since I have a calculator. .52 grams per cubic centimeter. So that's how you measure the density. So it's going to be the depth divided by the height of the object will give us the density. And that is how you find the density of an object that weighs less than that. Now keep in mind, this is why, like an iceberg, when you see a part of it above the surface, because the density of ice is 90% that of water, 10% is above the surface of an iceberg, 90% of it's still buried. I mean, there's one problem with the Titanic, is you had a little bit showing, but most of it was still below the surface. So that is section 10.7. What I'm going to do next, on the next lecture, is finish up with pressure, fluids, airplane wings, Bernoulli's principle. So that's chapter 10, lecture 8. Okay.